Okay, so stuff's out of date. Some of the stuff is just simply plain wrong. Now, why are things wrong? Well, we all make mistakes in life, even I do. Right, occasionally, like forgetting to mark your draft 7100 reports and having to be reminded. Thank you for whoever reminded me. Yeah, so we're all prone to human error, and we are all prone to believing false things and delusions and putting them up potentially online for everybody else to read. I wasn't aware until the other day about how many young people believe that people like Beyonce and other pop stars are members of the Illuminati. That was an interesting discovery the other day that I made. Maybe I'm delusional, maybe they are, I don't know. And then there's deliberate falsehoods. People put up wrong information. There are liars, malingerers. I'm not quite sure we've got malingerers. Malingerers probably can't be bothered to put anything false up online to make it worthwhile, and vandals who go and destroy things. There are people, these may be politically motivated or purely motivated by entertainment. So there's a lot of false information out there. And there are genuine disagreements. We don't know everything about everything, unsurprisingly. So, for example, the International Astronomy Union says Pluto is not a planet, but the astrologers say Pluto is a planet, and they fundamentally have a different perspective on whether Pluto is a planet or not. And the other thing is, in an open world, in an open system, you never know whether you've gathered all the information about a topic or not. There's always more out there. So you have to sort of take a cut-off point and say, I've got enough information about something. So, having said that, a semantic web, what is it? Well, it's an attempt to rather have a web of documents, like the World Wide Web, but to have a web of data. That's the idea. So we're taking the data out of the documents and freeing it and interconnecting the items of data rather than the documents in which that data is embedded. Yeah? Free the data from the documents, that's the idea. So we're basically separating, as I said on the one, separating the data from its presentational context, which is the document. So just like CSS separates the presentation, the styling of a web page from the content of the web page, this is separating the data items out of the page from the style in which those data items are presented. And that style may be, it's presented as a table. That's a style of presentation. It's data structure. So instead of web pages pointing to each other, data items point to each other. And this is another great invention by Tim Berners-Lee. He should have a double Sir Tim. He should be Sir Tim or something for this, because not only has he invented the World Wide Web, he's the inventor of the Semantic Web. And that's the original item in which he proposed this data model. AAA, the problems of AAA still exist with the semantic web, but the idea is that the semantics, and I'll explain semantics a bit more in a minute, provides the information that allows users to address some of these issues. So we're putting semantics onto our data or embedding our data within a semantic framework that allows us to do things like identify who made a particular statement, for example, and things like that. What is semantics? It's a word we throw around, and even after, however many years of thinking about this, I still have problems in my head sometimes, doubts throw in that I really don't understand what semantics means. But there's semantics, what it means as a word. versus how it's implemented in computer systems. And I think that's where my doubts lie in whether a particular computer implementation is truly semantic or whether somebody's just used this word semantic and attached it to something that is perhaps not very semantic. Okay, so what is semantics? Semantics is meaning. So let's contrast that with syntax. So syntax is how we organize something, how information is structured, basically, the syntax. So JSON is a syntax. XML is a syntax. It allows us to, it's a way of writing, structuring information. The relational model is syntax with all the conditions. If you've got conditions and relationships stated, this is all syntax, it's structure. There is no meaning behind the data in a JSON file or an XML file inherently in the numbers and letters stored in the file. The meaning is what we understand the data to actually be telling us. So semantics is what that information means. And semantics is closely linked to the concept of ontologies, or to be honest, it's being implemented through an ontology. What's an ontology? I think we've mentioned them on several occasions before. They are models of the world based on some kind of semantic statement. Something is something else. Something is a type of something like that. As with most of these things, we'll see some examples, and hopefully this clarifies this a little bit more. Ontologies, formal ontologies, are basically a set of statements. Those statements, there may be rules, like you have in relational databases, constraints, imposed upon these semantic statements to impose validity on those statements. Certain statements we know can't be true, for example. Or we know that this statement, if we make this statement, it infers another statement. Okay? So we can constrain what is allowed as a valid statement. Once we've got this list of statements, then we can run algorithms across them that facilitate explanation, extract meaning, extract pattern out of these statements, which allow us to infer and make predictions, a set of rules, if you like. And one of the things that we can, or one of the benefits of developing a formal ontological model of a problem is that if you've got different people with different viewpoints on a real-world issue or problem, then the act of creating one of these ontologies, writing a set of statements and defining the constraints upon those statements is a very useful way of mediating and focusing people's thoughts on what are the common factors of a particular problem, or what the factors actually are, how to divide a problem into its parts. So it's a helpful way for mediation. So in another life, I sat around quite a few tables and we would have a group of geneticists, a group of paleontologists, maybe some people who are experts in tree builders and some ecologists, and we'd all sit round a table for 2 days and we would spend our time trying to talk to each other about, for example, the evolution of ecology across organisms through time and space and things like that. Half the time, or more than half the time, was spent just developing a common language which allowed us all to talk to each other. Because, for example, a geneticist's view of a gene may be very different from an ecologist's view of a gene or a paleontologist's view of a gene. paleontologists rarely have to deal with genes after all at all. So it's a good way if you've got different people, different groups of people with different interests in the same problem to come up to talk to each other and develop a formal way of defining what your objects are and what the relationships between their objects are. Okay, so this lecture, what am I going to do about the semantic web? The data structures and the syntax of the semantic web, the query language of the semantic web, the geosemantic web, throwing geography on top. I don't know why I've got mapping the internet there. It should have been taken away. We're not doing mapping the internet. That was an old lecture, so ignore number 4. So the basic unit of the semantic web is what is a triple. We met triples last week, I think it was, in regarding to tagging of things like photographs and things like that. So the semantic web is built on triples. That's your basic item of information. And triples are generally, well, there's a number of different ways in which we can write triples. There's different syntaxes for triples. But within the semantic web, we use what are called RDF triples, RDF standing for the Resource Description Framework. Don't worry about the details of it. But under RDF, a resource is anything we might want to talk about or we might want to communicate about. So a resource could be Shakespeare, Stratford, the value of X, all the cows in Texas, buses in Kingston Town Centre. It's the subject, the thing that we're interested in, we're making a statement about. So that's where the resource comes from, the word resource in RDF. But if we remember from last week, we've got a basic 3-item structure to a triple. We've got a subject, which is the resource, a predicate, and an object. So it's like the triples we had last week, but the triples with slightly different sort of wording associated with them. So for example, Shakespeare wrote Hamlet. We're going to do a lot of Shakespeare today, simply because the book, the easy to access book on the semantic web, these are the examples that come from it. So Shakespeare wrote Hamlet is an example of a triple. And a triple, as we can see, is a directed graph. Shakespeare wrote Hamlet. Hamlet didn't write Shakespeare. Yep, only goes one way. It's a directed graph. So if we break down all the information we have into triples, we have a whole pile of these mini directed graphs. The basic concept is you take a whole bag of graphs, mini graphs, chuck it into a big barrel, and combine all these mini graphs into one large, or as many large graphs as you can, by combining the items in your triples. So every time we find Shakespeare, we match it to other instances of Shakespeare, and we can create a large graph. And when we've got a large graph, and we've got semantics, like wrote is a semantic statement, then we can make reason across the graph that we create. So this is a graph database model. Triples and tables. Okay, so most data comes in tables. That's the most common format. Not all data by any means, but a lot of data is stored in tables. So here we are, Elizabethan literature and music. Simple tabular format, as you like it, written by Shakespeare. It's a play and a year, 1599. Green Sleeves, written by Henry VIII. It's a song written in 1525. How do we turn these into triples? It's very simple. What we can do is we simply make statements like Shakespeare wrote King Lear. So King Lear, well, we don't actually have King Lear in that. That's just typical, isn't it? Shakespeare wrote Macbeth. So we're taking the author, the concept of writing, which isn't in the table but is inherent to the table. The table is about who wrote what, after all. So the very title, all these items in this table, or the relationship between author and title is always wrote. The relationship between title and year is always date written. There is no relationship, direct relationship between author and year except through title in this table. And medium is dependent also, well, it's not dependent, it's a, yes, it is dependent on the title and what the thing is. So, As You Like It is a play. So we can take all these combinations of columns and basically turn them, take a column, set of columns, and decide what is the semantic relationship between the items in those columns. Shakespeare wrote King Lear. Shakespeare wrote Macbeth. Anne Hathaway married Shakespeare. Shakespeare lived in Stratford. Stratford is in England. Macbeth is set in Scotland. England is part of the UK. Scotland is part of the UK. Now, clearly, there's more information here. In fact, I don't think any of the information in this set of triples is in this table here. So it's a slightly dodgy arrow, but I think you get the principle. We can extract the data out of data tables, turn them into triples, and create a whole list of these triples with different relationships between the different predicates and objects in our system. And we have this list of triples, then we can start building a graph out of this list of triples. Shakespeare wrote King Lear. Shakespeare wrote Macbeth. Shakespeare is the subject, exists, well, Shakespeare exists here. Shakespeare exists here. He also exists there as the husband of Anne Hathaway. If we take all our instances of Shakespeare in our triples and basically collapse them into one node in our network. So we've got 4 Shakespeares here. We've got one Shakespeare node called Shakespeare. And Shakespeare, we can see the relationship with Anne Hathaway. Anne Hathaway is married to Shakespeare. Shakespeare lives in Stratford. Stratford is in England. England is part of the UK. Shakespeare wrote Macbeth, set in Scotland, part of the UK. Shakespeare wrote King Lear. Yes?
I thought you said they had to be directional. Surely Shakespeare's also married to Anne Hathaway.
Indeed. Good point. We will return to that at a later moment. At the moment, yes, there is information that we can infer from this graph because we know what married means. But with your standard RDF, it is a directed graph, and we would need a second triple that says Shakespeare is married to Anne Hathaway, and then we would have a link going back that direction. Clearly, though, that is duplicating information, and as we know from the relational part of the course, we tend to avoid duplicating data wherever possible. We'll get onto this issue in due course. Okay, and you can see, hopefully, that we can start actually making rationalizations across these graphs. Okay, we often have several different sets of triples from different places. We can gather these triples from wherever we like. Some triples from over here, some triples from over there, some triples I had in my bottom drawer, stick them together. So here we've got 2 sets of triples about different things because people collate databases of triples about particular subjects. So here's a database of triples about parts of the United Kingdom, saying which the names of the subparts of the United Kingdom, identifying that they are part of the United Kingdom. Whereas this graph is mostly about Shakespeare and Shakespeare's plays. Okay, it includes England and Scotland here because those are answers to some of the questions being asked or the statements being asked, but it is not inherently a set of triples about geographic places. But if we want to combine and to infer more than we just have about where somebody lived or where a play was set, and we wanted to infer more things about the UK, for example, then we could combine this set of triples with this set of triples on the UK, and suddenly we can infer a great deal more about the geography of Shakespeare's plays than we could just from the triples that we have, the play triples. Whenever we merge a graph, a triple graph, we've got a problem. And that problem is one of the ones that go issues that we have with AAA. Remember my name. My name can be, I can write my name, and I do, in multiple different ways. How do somebody else know that I'm I? Or that DM Kid is the same as David Michael Kidd, who's the same as Dr. Kidd, and what have you. So this is a fundamental question, especially when we're drawing data, sets of triples, from potentially completely different places. This was not collated by the person who collated this. It was collated for a very different set of reasons. How can we guarantee that the concept of England is the same in both sets of triples? That may seem a trivial question. Let's have a little bit more of a, I just thought of a slightly better one. How do we know that Stratford is Stratford in, is it Nottingham? I can't remember which county it's in. Stratford. Anyway, where Stratford-upon-Avon, where Shakespeare lived, and it's not Stratford in East London where the Olympic Park is. Those are fundamental questions. So if we've got a whole load of triples about the geography of England, we might have triples about Stratford in London. So we've got a problem there. We've got one node called Stratford referring to two different things in the real world. How do we uniquely identify that what a node in the graph is referring to? Well, the way we do it is we identify the node with a URL or a URI, a global unique identifier that points to a definition of what the thing is that we're interested in on the web. So our URI or a URL would point to a definition of what we meant by Stratford in this case, whether it's East London or whether it's Stratford-upon-Avon. And if both nodes in the two sets of graphs that we're putting together point to the same URI, then we can assume that they point to the same concept of Stratford. And therefore we can collapse those nodes. If they point to a different URI, then we assume that they're different unless we go and follow those URIs, read the descriptions and see whether they're the same, or we can equate them, in which case we can collapse the node. Otherwise, we know the nodes are potentially different definitions of the same word, same concept. So here we've got the merged graph from those two sets of triples, and we can see that we've got, well, that's just the combined graph of those two, and we can see the link. Shakespeare lived in Stratford, and now we can see that we've got the Stratford is in England component linked in because we've collapsed all the Stratford nodes down to one node. So we can build up these graphs. URIs or URLs are potentially very long. And if we're exchanging data over the internet, we don't like long strings because suddenly our files are 3 times larger than they need to be. So URIs in triples can be or are often compressed and written in a shorthand which is called Q names, or considered as Q names, which is a shorthand. Q names provide a shorthand for URIs for triples. Now, try and remember how all this works. Okay, so a Q name has a namespace, an colon, and what's called an identifier. So something like geo, remember namespaces, geo, namespace, England being the definition of England in the geo namespace. If we have these, we use this to identify a node, to specify what a node is, and then we know where the definition of the geo namespace is. All we need to do is have a declaration in the head of our file full of triples that says, when we're talking about geo, look at this URI, and there's all the definitions for the geo, for the objects in the geo namespace. So rather than including the full URI in our triples, we can use this shorthand QNames and then have a pointer at the top of our file like we do for the links and to JavaScript files and CSS files that points to where geo exists. And there's just QNames have a int capital convention, camel case convention for defining names. So QNames, if we turn our tables into a QName structure, so we're basically adding, so we're now talking about Shakespeare as defined in the lit namespace, wrote being as defined in the lit namespace, as you like it as existing in the lit namespace. So all these things are defined in the lit namespace, and we're pointing, saying our predicates, our subjects, our objects are all defined in this lit namespace, and that's the definitions we're using. And in this example, lit points to this address here, which is where the definitions of those objects are. And as you can say, this is actually comes from a book called The Working Ontologist, which is where all these examples come from. And if you want an accessible read on the semantic web, that's a good book to start with. And basically, I'm giving you a sort of synopsis of some of the stuff in that book. Okay. There is a namespace called RDF namespace that defines the objects that are used in the RDF file description. And it is a W3C standard, along with some other namespaces like RDFS, OWL, XSD, XMLS, and other wonderful exotic objects, which we'll see some of in due course. So there's a whole load of namespaces defined by WC3 that define the fundamental or the most commonly used predicates, mostly, that are used in triples and defining semantic web graphs. So, for example, the RDF namespace defines concepts such as type of something, subclass of, class, inverse, and property. So it defines these, excuse me, these are mostly predicates. So we take our playwright table now. Now we have got Shakespeare as defined in the lit namespace. Is a type, Shakespeare is a type, and we're defining type as defined in the RDF namespace of playwright as defined in the lit namespace. Ibsen is a type of playwright, Simon is a type of playwright, etc., etc. So instead of defining our own lit predicate, we're using a standard RDF predicate for it. Down here, we can also do things, what are we doing here? Biz, defining types of names. Okay, we can also define, playwright is a type of profession is a type of composition. Okay, I think we can see here we can define additional chains. So a playwright is a type of profession, and a profession is a type of compensation. So we can start building our own class structure or relationship between our predicate objects. We can create our own predicate objects based on existing ones. The RDF property predicate, for example, indicates that a resource should be used as a predicate and not a subject or object in an RDF statement. So this is starting to put controls on where you can use these triples within a set of, these Q names in this case within a triple. Okay. So wrote, the literature wrote, the word wrote in the literature namespace is a type of property. It can only be used as a property. Geo part of can only be a property. It could never be a subject except in this set of definitions. Only in this set of definitions can it be, but once we've defined it as a property, it can only ever be used as a property. A property being a predicate. Yeah. So we're now starting to constrain how we can use these items in our triples. So how do we write these triples? We need a syntax to write them. And there are a number of different syntaxes or serializations. Serialization is just another word for a sort of how to write something out as a straight long line of characters. So, for example, there are a number of syntaxes. N triples is probably the most expansive. So here's our predicate pointing to a URL. Here's our, sorry, not our predicate, our object. Oh, God, my brain is really. Here's our subject, predicate, object. I should have written that on the board at the back so I could not forget it. Predicate, oh, God, I forgot subject, predicate, object. Subject, predicate, object. Subject, predicate, object. And if we can write this, it's a, whatever that is a creator. So the creator of this, the RDF core, triples definition is Dave Beckett. I think that's the way we read it. And another creator is Art Bairstow, etc., etc. So a list of triples as URLs like that, but you could also replace it sometimes with just text like that. There's a slightly shorter, this is a very long-winded syntax, as we can say. There's a lot of repetition here, a lot of repetition. As we know, we try and avoid repetition to have small file sizes. So there's another other notations. What's called 3RDF, or known as N3, is a slightly more human readable form where we've got, can put little letters in, aliases, as use aliases for pointing to a particular URL, and then we can write a set of triples like this. So here we've got a number of triples. We've got 3 triples with the same subject. So we've got a subject, then we've got a predicate 1 for that subject, and an object for that predicate. Then we've got a predicate 2 for that subject, and a object 2, etc., etc. So this gives us a shorter and more human readable form for exchanging the information. There is also an XML version, just to make you happy, called RDF XML, where we've got our pointings to our various namespaces here. This is where this XMLMS comes in. So we point to our definitions, and then within here we've got an RDF. We've got our first description, that's our object. Then resource equals, trying to get my brain around this, titles. I'm afraid that's escaping my brain at the moment. So it's RDF, this will be the object. Then these will be the about equals. Right, can't remember how that one works, sorry. My brain is giving up on that. Okay. But it basically does the same thing in a different way. Linked data. So there's all these different ways, different syntaxes of presenting data, defining data on the semantic web. Which way, what's the best way of doing it? Because there's a variety of different approaches, syntaxes, as we've seen. So in 2006, good old Tim again came up with the idea of linked data. And linked data I understand as basically Tim's suggestion for best practice for the semantic web. A set of rules for following. What's the best thing? How do we get this semantic web working? Well, one thing that is list of 4 things, use URIs as names for things. So none of this putting text in quotations or whatever. Everything should be a URI. There should be nothing that isn't a URI in an RDF file. And they have to be HTTP URIs as opposed to any other type of URI, so people can actually look these things up. When somebody looks up a URI, it has to provide actually useful information at the end of it rather than just being a blank space, that it points to a blank space. Because effectively, as you know, you're pointing the same blank space, you're pointing to the same thing, but you don't know what that thing actually is. If you don't have a good description of what the thing is at the end of your pointer, you're still in the same problem in that you don't really know what the object is that you're doing this. And the other thing he's got is include links to other URIs so that they can discover more things. Well, I'm not really, can't say I'm able to pontificate on that one anymore, just to read it. Good question. Again, we will get on to that in due course. Where does this used? Exactly. It is starting to be a real application, and there are certain places where you have to use being run on semantic web. We'll have a break in a couple of minutes, or in a minute or two. This is a diagram of the present, or well, probably it's August 2014, so we're 3 years out of date now. And this is the LOD cloud, basically the linked data cloud. This is not all linked data triples. This is links. These are the organizations that publish data as linked data following Tim Berners-Lee's description of what linked data should be. So it's not comprehensive of all the people who publish RDF, but just people who followed his standard for semantic data. Now, clearly you can't read that from the distance you're at, but probably you might be able to read DBpedia in the middle, which is I'm not really up on, but it's some sort of, if I understand it correctly, it's Wikipedia exposed as an RDF, in RDF format, if I'm correct there. Geonames, a giant list of place names. Just looking at the colors, we've got a huge area in green, which is to do with publications. Now, RDF, the word resource description framework, the resource part comes from library descriptions of what things are on the internet. Libraries refer to resources. So it has a strong backing from the library community. The library community were part of the people who initially sort of set this up and were interested in it. We've got a large section in sync here of life sciences. Social networking uses it quite a lot. So you can get linked data from various social networks. Here's our geography strand, rather thin. It's not an area, huge area when we're looking at that. The area over the far side is government, so a lot of government data being published in RDF nowadays. It's an overall picture. How many triples are there across this graph? Billions is the answer. So if you want a network graph with 1 billion triples, you can extract it out of these organizations. Right. Should we have our break? Yeah. Okay. How long do you want?